In this question, we have a pipe. It says it's in air. That's telling us right off the bat that we can use V equals 343 meters per second. We're asked to find the frequencies of the first two harmonics if the pipe is open at both ends. Okay, so the way I'm going to start this is I'm going to start by drawing my first two harmonics. So I'll draw my pipe. I'll have it open at both ends. Since I want to draw two harmonics, I'll draw two pipes, even though I know they could both be in the pipe at the same time. I'm going to choose to draw the displacement waves, and what I know about a displacement wave is that it has an antinode at each open end. You could just as well be asked to draw the pressure waves where there would be a node at each open end. So in my first wave, I go from an antinode back to an antinode. And if I look at this picture, I know that the length of my tube is 2.46, and knowing this is going to help me figure out the wavelength. The way I do that is I notice I go from a crest down to a trough. That's a half of a wavelength. 1/2 lambda equals L. That tells me that lambda is 2 times L. 2 times 2.46 is going to give me 4.92 meters for my wavelength. To find my frequency then, I know V is equal to F times lambda. That tells me that F is V divided by lambda. V is 343 meters per second. Dividing that by 4.92 meters, that gives me a frequency of 69.7 hertz. This is the first frequency in the tube. This one is the fundamental. For my next frequency, I know I need to draw more wave in the tube, so I'm going to go from an antinode to an antinode, but I need another antinode in between. So this time my wave looks more like this. Okay, so there's my wave in the tube. This time I go crest, trough, back to crest. This is a full wavelength. So this time I have that lambda is equal to L. That tells me that lambda equals 2.46 meters. And then my F, which is going to be V divided by lambda, 343 meters per second, divided by 2.46 meters, is 139 hertz. Okay, there's the first part done. Second part, what would be the two lowest possible frequencies if we cap off one end of the pipe? So then how do things change? So I'll grab a fresh sheet of paper and we'll have a look at this one. Let's keep the question visible and I'll work underneath. And I think I'll work on doing those side by side. So I'm going to draw my two pipes. And I know one end is closed. I'll shade in the closed end. That's the custom. I'm going to draw my displacement waves for both of these. I know I have an antinode in displacement at a closed end. So my first wave, the fundamental, would look like this. For my next wave, I have to squeeze in a little bit more. I've got to get another node in there, and it's going to look like this. Let's look at the fraction of a wavelength now. I go from node to antinode, or from equilibrium to crest. That's 1/4 of a wavelength. For this one, I go from an equilibrium to an equilibrium. That's 1/2 of a wavelength. And then I get another 1/4. This one is 3/4 of a wavelength. Alright, now I can find my wavelength in each case. This one, lambda is equal to 4 times L, 9.84 meters. For this one, lambda is 4L over 3, equals 3.28 meters. My frequency is V divided by lambda, 343 over 9.84, 34.9 hertz. For this one, F is V over lambda, 343 over 3.28 to get 105 hertz. So that's how our frequencies change when we cap off the one end. So let's move this one out of the way and let's look at the next question. This question says we're making a primitive musical instrument with a wire and a mass hanging from it. So this is a long wire. We're going to think of that like a string, and then we're hanging some mass from the end. First of all, sketch the fundamental resonance for this instrument. Well, our fundamental resonance, this is going to be like a wave on a string. We know that on a string we're going to have two fixed ends, fixed at the ceiling, fixed where it hits the mass. And for our fundamental, that's going to be the wave that looks like that. So there's our fundamental, there's part 1. For part 2, we want to get into a calculation now. If the string has a length of 1.2 meters and a mass of 8 grams, what do we have to have for this hanging mass to get the fundamental resonance to have a frequency of 56 hertz? So this is going to have a frequency of 56. What does that mean about this mass? So let's write down what we can think of that might help us solve this problem. I know that the speed of that wave on that wire is given by F times lambda, and it's also given by the square root of tension divided by the mass per unit length. This is pretty good information. My frequency is 56 hertz. I can get my wavelength by looking at this string because I see that I have a half of a wavelength on this string here. I know that my tension is a result of this hanging mass, so my tension and my mass come together. Mu is the mass per unit length of my wire. I know the mass, I know the length, so I can find mu. So I think I can use this equation to figure out that mass. I'm going to start with finding my wave speed by using F lambda. So I know that my F is 56 hertz because that's given to me. For my lambda, let's look at the picture. This is my total length of my string, and I see that that's 1/2 of a wavelength. That tells me that lambda is going to be equal to 2 times L. So lambda equals 2L equals 2 times 1.2 meters equals 2.4 meters. So now I can calculate my speed. V equals F times lambda, 56 hertz, times 2.4 meters equals 134.4 meters per second. Okay, I've got my V. Next, why don't we get our mu? Well, mu is the mass per unit length of our wire, so it's going to be the mass of the wire divided by the length of the wire. 0.008 kilograms, that's 8 grams converted to kilograms, divided by 1.2 meters, gives us a mass per unit length of 6.67 times 10 to the minus 3 kilograms. Okay, now we're kind of cooking. Next, let's figure out something about the tension, because we've got this part, we've got this part. What are we going to do about that tension? Well, we said that the tension in the wire is produced because we've hung a mass off it. Let's draw a free body diagram on that hanging mass. We have the tension holding it up. We have the earth pulling it down, that's the weight. We know that the sum of the forces in the y direction is mass times acceleration. It tells us that T minus W is mass times 0 because it's not moving up or down. So T equals weight equals M times G. So we definitely see that our T and our M go together. If we could use this equation to figure out our T, then we could use this equation to figure out our M, because M is going to be T divided by G. Okay, let's use this equation and let's figure out our T. Since V is the square root of T over mu, if I square both sides, I'll get V squared as T over mu. That means then that T is equal to V squared times mu. I know my V, that's 134.4 meters per second. Got to square that, multiply by my U, 6.67 times 10 to the minus 3 kilograms. And I get a tension in my wire of 120 newtons. Now I'm all set to come back up here. I recognize that my mass is my tension divided by G, 120 newtons, divided by 9.81 meters per second squared, gives us a mass of 12.3 kilograms. So that's how we make that primitive instrument.